So Adam is one of the most popular algorithms or optimization algorithms in the whole of deep learning literature. As of 2018, this is the most popular deep learning optimizer. This is the most popular. Okay. So the core idea behind Adam is this, right? If you recall our ADA delta, in our ADA delta and even ADA grad, we are storing, sorry, in our ADA delta, we are storing the exponential weighted averages. We are storing the exponential weighted average of squares of gradients, right? Of gradient squares. And we're using this to modify our learning rate, right? Through eta dash t, right? But here, look at this. We are taking the squares of gradients and using it. The idea here is instead of, or in addition to taking the squares of gradients, what if I store, right, the exponential weighted average, I'll just write it as EWA or exponential decaying average. Okay, so let's write it as exponential decaying average or exponential weighted average, right? Instead of, so in addition to the squares, what if I use the exponential decaying average of GT also? So here we are doing GT squares. What if I use the value of GT itself, which is the gradients? So in addition to gradient squares, exponential weighted average or exponential decaying average, like in ADA delta, what if I use the exponential decaying average of gradients themselves? Okay, and there is a lot of research. I'll come to the research which shows that Adam is the fastest way to, is one of the fastest algorithms as far as convergence is concerned, right? So let me write it down. And the Adam actually stands for adaptive moment estimation. Okay, I'll explain you why it's called moments. So in statistics, right, mean is often referred to as a first order moment. Mean is often called as a first order moment in statistics. Variance is referred to as second order moment. Okay, in mean, so I'll write the exact definition. You can think of the exponential decaying average of the gradients as sort of like computing the means. It has the same connotation, same idea of a mean. When you take mean squares, when you take gradient squares, what you get is the second order moments of your variance, right? So that's why it's called the moment estimation, because you're taking both the first order moment. This is sort of like mean. The exponential decaying average is sort of like a mean with exponential decay, right? The exponential decaying average of GT of gradient squares is like the variance of your gradients, which is a second order moment. That's why it's called moment estimation. Okay, in statistics there is this term called moment. First order moment is mean, second order moment is variance. So let me write down the equations for you. Okay, and I'll explain one by one. So the mean at time t, okay, corresponding to the first order moment, is beta 1 times mean at t minus 1 plus 1 minus beta 1 times gt. Very simple, right? Similarly, variance at time t is beta 2 times variance at t minus 1 plus 1 minus beta 2 times gt square. Very, very simple definitions, right? Remember, here your beta 1 lies between 0 and 1. Your beta 2 also lies between 0 and 1. Typically, beta 1 is taken as 0.9. Typically, not always. These are good values. And beta 2 is taken to be 0.99, typically. Okay, so what are we doing here? This is nothing but exponential decaying average of means. This is exponential decaying average of your just GTs, of GTs. This is exponential decaying average of GT squares. Okay, if you don't have exponential decay, just average of GTs is what? Is mean. That's why we write it as MT. The simple averages of GT squares is nothing but your variance, right? So the only difference between simple average and exponential decay average is basically this weighing beta and 1 minus beta and this recursive definition that mt is represented as mt minus 1. Okay, so these are first two equations. Let's call this equation 1 and equation 2. The third equation is, it says m hat, so let me write it in the same color. Okay, m dash t or m hat t is m hat t by 1 minus beta 1 power t. This is power t. Okay, let me write it better, okay, so that it's easier for you to understand, right? Beta 1 power t. Power t. T is the iteration number. Let's not forget that. And v hat t is vt by 1 minus beta 2 times t. So beta 2 power t. This is exponent. This is power t. Okay, this is power t. Now your wt becomes wt minus 1 minus alpha times m hat t by square root of v hat t plus epsilon. If you look at this looks very much like your Ada delta and Ada grad, right? This looks very much like your Ada delta and Ada grad, except that, okay, so let's write it down. Okay, if your beta 1 equals to 0, then what happens? If beta 1 becomes 0, this whole term becomes 0. If beta 1 becomes 0, what happens to your mt? Your mt is nothing but gt, right? So you have your gt here. Okay, you have gt by variance square. Then what do you get here? You get your Ada delta. You get your Ada delta if beta 1 equals to 0. If beta 1 equals to beta 2 equals to 0, then what happens? So if beta 1 equals to 0, this goes off. If beta 2 equals to 0, again this goes off, right? If beta 2 equals to 0, this also goes off, right? You just have squares of sums now. Beta 2 equals to 0, you're left with gradient gt squares, right? But these gt squares will remain, isn't it? So in a nutshell, what happens here is, okay, let's see what happens. If beta 1 becomes 0, sorry, if beta 1 becomes 0, yeah, this term goes off, so you're left with this. This is not exactly like an Ada delta or anything like that, but this is related to Ada delta. When beta 1 becomes 0, what you get is Ada delta, right? Except that this whole formula, if you think about it, okay, let me walk you through step by step. The first step here is you are computing the exponential decaying average of your gradients. You're computing the exponential decaying average of your gradient squares, okay, and you're correcting them here. In statistics, this is called bias correction. Okay, you're slightly correcting them, you're modifying them because you've used beta 1 and beta 2. Finally, what am I doing here? I'm doing very much like my Ada delta and Ada grad, right? It's very similar. It's very, very similar in concept to that, right? So this is called Adam. And in typically Adam, this alpha is taken as 1. Typically, beta 1 is taken as 0.9, beta 2 is taken as 0.99. In standard libraries like TensorFlow and Keras that we will see in the next chapter, these default values are used extensively. Again, Adam has all the advantages. Adam has all the advantages that you see in Ada delta, right? That it converges fast. You don't have to worry about fine tuning so it has all of these advantages. Let me take a few steps back. No need to manually fine tune, sparse and dense features, it works. You don't have to worry about slow convergence. All of it works well. And Ada grad was discovered experimentally. So in this section, in this section for this chapter or for this video, in the description section, I have added a reference link to the actual research paper. This research paper was published in the December of 2014, the Adam research paper. Okay, this is the Adam research paper. And one of the very interesting plots in the research paper is this. This is basically iterations over entire data set, which means this is your epoch number. This is your epoch. This is your training cost or training error. You can think of it as training error. Right? So what happens here? Right? What happens in your case is, if you notice, your this line, this purple line that you see here corresponds to Adam, which means if you have done 50 iterations or 50 epochs, right? When you've done 50 epochs, and remember, this is 0, this is 10 power minus 2, this is 10 power minus 1, and this is on MNIST data with a dropout layer, right? And when you have 50, when you have had 50 epochs, what's happening here? The cost or the error, the training error that you get with Adam is significantly lower than the training error that you get with all other variations like AdaGrad, RMS prop, SGD with Nesterov, and Ada Delta. So Adam, even in lots of experiments, has shown to be extremely fast, and it works very well. So my personal preference, right? If I have to choose an algorithm, Adam is one of the best algorithms that I choose. In the next video, I'll explain you various cases in which we'll understand which algorithm or which optimizer works better in which case. That we'll see in the next video.